So hi everybody. I guess we are going to get started. As I say in the chat, I will be monitoring the Discord chat as well as the Zoom question. So don't hesitate to ask your question on either points, and I will gladly answer them at the end of the talk. So welcome to my talk about designing C++ tools in C++20. This is a talk that I already co-presented with Denis Jarozewski, and this will be my solo outing of this version of the talk. So if you want to follow along, there is a link if you want to follow on the slide at the same time. And we are going to have a look at what's going on in this talk. So, as the title actually spoiled it a bit, we are going to speak about SIMD programming. But let's get a bit of context before, and let's turn that into some kind of elevator pitch. Okay, so let's say you need to do some operation, like you need to find a value in a bunch of bytes. Let's say 1,000 bytes. You are, I don't know, looking for 0 or something like that. And to do so, you want to do this research of 0 on different times. So your 1,000 bytes is either actually 1,000 char or 500 short or 250 int. And if you do some measurements, you got those timings. Okay, and you see that we have this nice slowly decreasing curves. That basically tell us that the bigger the chunk you are looking at, the faster you got. This is all nanoseconds, okay? And we go between 240 up to 70 something for those. But in fact, we can do far better. We can do far better with an implementation that basically stay at around 8 something nanoseconds, which leads us to a speed up of roughly 9 for the int, and roughly, how much is that? 30 something? 30, yeah, 30, how much is that? Yeah, a lot, you see. Times 16 is probably 32 or something. So we can actually do far faster. But the actual question is it the fastest we can do? I mean, yeah, we are better, but is it actually better? There is a cool way to search for 0 in a bunch of bytes. It's calling Sterling, which is basically a highly optimized version living libc or libc++. It's most of the time and written in C/assembly, very fine-tuned and so on. And so this is the time we got for running on our systems using AVX2. So steady Sterling took about 8 something nanoseconds. And we are pretty much at the same level. Okay, this is noise. Okay, so we go as fast as an actual SRN with an actual high-level algorithm with a proper optimization. But one can actually say, finding something in an array that's rather a trivial task. What about something more complicated? Like an inclusive scan, for example. Okay, well, let's do the same. 1,000 bytes, different integer types. This is what STD inclusive scan is giving us, okay, around 200 something nanoseconds down to around 70, and this is what we can actually do. Again, speed up of roughly 4 there, 3 there, and a bit around 2 over there. So we can also accelerate those non-trivial functions. Yeah, but inclusive scan, of course, it can be vectorized. It's a numerical computation. Yeah, what about something more complicated then? What about remove if? Remove if takes a bunch of bytes there, predicates, and it will push all the values that doesn't fit the predicate at the end of the block. So we are actually moving conditionally some values around. And so usually when you want to bench stuff like remove if, the interesting metric is not much the size of the data block or whatever. It's how many elements are going to be moved around. So you could have a very simple task where nothing is actually going to be moved, nothing to be moved, or everything has to be moved. That's the best case. And we have this nice kind of bell curve around 50%, nice symmetric things, because as you go close to the 50% mark, you keep trashing more and more your branch predictor up to the worst point at 50%, where we are like 25,000 nanoseconds for char, 8,000 and 1,400 for int. And then you go down again because your branch prediction starts to be better. Let's focus on the char one first. If not, we won't see anything. And actually, this is something you can vectorize if you have the correct tools, and you end up with this. A nice branchless implementation that just got the same speed, whatever the granularity of the value to be moved is. And in the worst case, we got like twice faster or 4 times faster, and the base case is basically 25 times faster. And if we look at all other types, we got the same shape, even for large types like int. Which is a bit less, symmetric because reasons, but we still have this time 3 times 4 speed. So it ends up that we can actually write high-level C++ code using non-trivial algorithms that behave as fast as they should. And what we will be speaking about here how we get there. So what's Eve? Well, Eve is a SIMD library. And so the next question is, what is SIMD for people that may not know exactly what's going on? Well, SIMD computation is a way to apply instruction level parallelisms to different operations. And it's usually put next to what we call SISD computation, which is a classical sequential style of CPU. So usually in the SISD, single instruction, single data processes, you have one stream of instruction that get paired with one stream of data, and that every other cycles produce a stream of one result each time an instruction is applied to one data. What SIMD does, it does the exact same thing. You got one and unique stream of instructions that get applied to multiple data at once. It can be anything, but usually, normally, in regular modern processes, those multiple data are gathered in what we call a wide register, which is basically a register which is 128 up to 512 bits and contains between 2 and 64 elements, depending on the types. And whenever an instruction is issued in this system, it will get applied the same way to all elements of the wide registers. And we get a wide registers as a result. And if everything goes correctly, what we expect is that the speed up of these systems compared to the other one is basically something along the line of the width of the registers, or the number of lanes, like we said. Usually to do this, you have different kind of tools. And it gets messy quite fast, because if I focus only on x86, we are basically looking at almost a dozen of variation of those systems, depending on the microarchitectures, the type of operation you want to do, the age of say microarchitectures. And only for the 128 bits, we already have like 5 variants, not counting the AMD variant. And of course, they all have different functions. The types they are providing are different. They are more or less retrocompatible within one architectures. But you cannot just say, okay, I will just pick one and go with it, because you will never know what your user will be using. ARM has the same system. It has something which is called Neon, and it's 64 bits compatible version. There is also SVE, but we won't be talking about that today. And PowerPC has some stuff also, a 128-bit instruction set called Aether, which is basically what's on Power 7 to 9 and probably 10 now. And there was a 256-bit version on the supercomputing systems. Okay, fine. I've got choice. That's good. But maybe I just don't care. I can just pick the lowest common denominator, write my code using this, and it will be enough. The fact is that it's not enough all the time. Depending on the architectures and the instruction set you use, you may have widely varying level of performance. If we take again this remove if operation that we saw earlier, this is the sequential reference. You see that depending on which type of instruction set we use, be it SSE2 in blue or variant of AVX or SSE4 in red and green, you got basically between 1 and 2 times the speed that you should be getting. So we get almost 80% gain there, we get roughly twice faster there, and we got a bit more faster using AVX. So you cannot just say, I will just pick one and be, like go my merry way. You will leave performance on the table, and that's maybe not what you want to do. So, how can I actually get my hand into these systems? Well, you can try letting the compiler do its job, because generating code from a high-level piece of code into a low-level, specific architecture-specific entry-in-6 sounds like a job for a compiler, and it works. It works as long as you don't do anything too much fancy. Your types are simple, and you are not going overboard in terms of complex mathematical functions. And as soon as you do that, basically you are doing transform or transform reduce like operation. The compiler is doing a great job. It's a bit sometimes conservative, like you won't go over a given level of intrinsics until you ask for it. But for the simplest cases, it's okay. But what for the non-simple cases? Well, you can actually use pragmas like OpenMP SIMD pragmas, or use special compiler like ISPC. But then again, both of those tools will have their small caveat and preferred version of the shape of the code and how the code should be written. It may or may not turn your code into something which is not portable anymore. So maybe we can look elsewhere. Like, I don't know, maybe there is some stuff in the standard library or some standard library implementation, like HPX, for example, that has its own version of the unsec execution policy that is supposed since 2020 to kind of make your algorithms vectorizable. Again, sometimes it works, sometimes it does not. Depends properly on the quality of implementation of the support of this execution policy. Most of the time, it goes down to just try to force and apply the auto-vectorizer onto the code. May work, may not work. May be surprisingly not good. And again, usually it won't pick up the most efficient architectures. Well, okay, fine. Then maybe I have a very specialized problem and I can just pick up libraries that solve it because someone already made the efforts to vectorize it. Yeah, it happens. There is a lot of them. You've got stuff like Elite for image processing. You've got SIMD JSON for JSON parsing and so on. But you're stuck with whatever API/choice of architectures those library made. And if everything fails, well, you can just, write intrinsics by hand. So maybe some of you already did that, and then you got all my sympathy. It's not easy. It's not portable. The function name make no sense, and so on and so forth. So we need to get past that. It's not sustainable. It makes the reasoning about the algorithm very complicated because it's mixed with the actual very specific architecture-specific code. So it's not something you want to do. So what is Eve then? So Eve is a library which is supposed to try to solve these issues by providing a C++ wrapper around CMD intrinsics, but not in just a direct way, like, this is add and this is service and so on, but in a semantic interesting way. It means that what we try to wrap is proper usage of those intrinsics. And to do so, we provide different elements. We have a library of core types that will match over the best combination of SIMD registered type for a given task, operation and algorithms using those. And by algorithm, I mean standard-like algorithms. And we will also be providing building blocks for algorithms. So you can just use the random algorithm you want if we have it, but you can also use our laid out protocol algorithm building blocks, and you can actually build your own algorithm. And we have a lot of numerical functions ranging from the classical CMAT up to very advanced math function like like special functions, probability distribution function, and so on and so forth. Some of them being the only vectorized version of said function existing right now. We support, as in it works and is tested, all x86 flavor up to AVX512, okay, and everything Neon up to Arch64. And we have a partial support for PowerPC. It means that if the code is there, it's probably work. It's not tested more than that due to resources allocation for our test system, but it's partially support. And everything is a license under the MIT license, so that you can take it and play with it. What do we support? We need a C++20 compliant compiler, which probably means you need to have the latest Clang and GCC. There is no way to, I would say that. We are going to request the latest compiler up to the point where modules are usable. And at this point, we could have actually a point in time where we can actually start rolling out, I would say that, rolling out our planned release schedule. For people using MSVC, well, you can try. We do also. The MSVC Clang support is mostly there. We are trying to push that soonish. So I know that I say soonish on this slide since CPPCon, but yeah. MSVC proper is a bit more complicated. We are still battling against some inadequacy, but we are trying to go over the details and make it work. So let's have a look at what we are going to do with this library. So this is a small Godbolt example. Eve is available on Godbolt, so if you want to play with it without having to download everything, you can. So what do we have? We have this wide type, which is this wide register thing, okay? And, well, you can construct wide registers. So you can load them from memory, you can fill them with a constant like we do there, or you can construct them using your lambda function or callable object thereof. So that this callable object will just fill in every lane of the wide register with whatever value you can compute using the index of the lane and the size of the registers. You can display them on the standard output and whatever, and you can call operators and functions. So there we compute the product of x by y, so we will do a piecewise product of every element in the lane. And you can call the function, and there we call the quarter cycle cost function. I will go over that a bit later. So it's basically cost plus restricted to the first quarter circle of the unique quadrant, right? And so what's going on when we do this? So this is the SSE4 version. So we have like, let's see, 4 elements inside. So x is full of pi, and y is basically something divided by 60, okay? And so we got that. And then we do our x times y, and we do the cosinus of this, and we got something like this result. The other one is the AVX2 variant. So we compile the same code, no change, just change the compilation flag for selecting the SIMD intrinsic variant, right? So there we are compiling with AVX2. You could also use march or the newest GCC extended march discriminators. And when I'm using the float on AVX2, I have like 8 of them. So this is the results. And then again, I call my function and everything works the same. We have this current API stuff that let you know which API you are currently compiling for. It's also something you can print out so you know what's going on. And one interesting point that we kind of see there is that every function in Eve is a callable object. It's not a template function, it's an object. So we can actually pass them directly to algorithms, for example. So we can just say, I want to use Eve cost to do my transform. And as they are objects, we can pass them to other functions, right? And generate another callable. And that's exactly what we are doing there, using this quarter circle thing. So why do we need that? Most of the time when you are trying to write proper SIMD code, you have to choose between, should I go very fast, but my result will be like less accurate or whatever. Or I can do some more optimization, some more operation inside my function. I will get I will go a bit slower, but I will get like more precision or a better input range or something. And the problem is, for some functions, you have a lot of options to do so. So instead of, well, just choosing one and let the user deal with it, and whenever someone tells, oh yeah, but I really wanted this version, we say, yeah, well, too bad. We have what we call decorators. So decorators can be applied to function object, and they return you the same object, same function, with a slightly changed semantic. So what does f quarter of cost does? It returns you an object that will be basically cost, but it will be restricted as its input as the first part of the first quadrant of the unit circle. And anything outside that will make this function return none. And the cool thing is that the way you implement periodic function like cost and so on is that it's basically a phase of reducing the input and then doing some polynomial approximation. But when you are in the first quadrant of the unit circle, you don't need to do any reduction. So you just end up with some, multiplication, and then some multiplication addition. So we are basically doing some kind of polynomials there. This is the ARM version. But of course, sometimes you have more than that. Maybe you want to get the half of the unit circle. So you can just call it this way, and then we get another curve which is slightly bigger because we need to go back from the half circle to the quarter circle and do some operation and then do a better polynomial. And of course, you can just call cost on the full circle, and you will get another bigger piece of code. And if you remove everything, you can call cost. And in this case, we have a slightly different operation, which is that we will try to see if every element in the wide actually fits in one of the quadrant subfunction, and if all fits, we call the proper one. And if not, we will do some kind of mix match of the result, and we get a very large function for that. So we have the control over this kind of quality. So either on the input range, for example, you can also have square root, but you can call row square root, which is faster. You can call an exponential, but you can call a pedantic exponential that will handle the corner case a bit better at the cost of speed, and so on. So that's how we want to let people choose the proper implementation detail of the function. Okay, fine. Functions, and so on. But how does it work behind if I open the box? So here is a C++ library, and we are making heavy use of a lot of different C++20 features. And let's have a look at a simple function like the ABS function, absolute value function, and we see what's going on. So this is how it's presented usually. So we have this abs function, and we see that we have two things going on. We have a bunch of type requirements and concept first, and then we have this web of if const expr. So the concept, like read scalar value and x86 ABI, let us actually, for the concept to be sure that we are going into the proper function, like it should be, like wide of t n, have this absolute value of wide of t as this exact implementation only if t is an actual arithmetic scalar value, like a float or an int or something. But we also need to know that we are currently compiling for a system that actually supports x86 variant of a SIMD, and that the type I'm getting in is actually one of those. You can actually specify a size for your wide, and if the size is not the same as the native type you should be having, we will be emulating it. So if it's smaller than the required style, we still use the same storage. And if it's bigger, it's what we call an aggregated types, and it aggregates multiple wide registers. So this is to ensure that if we go there, we have a single properly set up x86 compatible SIMD register. And once we are inside that, we have this categorize function that will help us get information about what's going inside the type. Is it a floating point value? If so, is it 32 or 64 bit? How many lanes? Is it just an integer? Is it just unsigned? And you can actually use this category with if const expert to just lay out every possible case we need to take into account. And that lets us go rather in a precise way where we want to be including subvariant optimization or global trivial cases like this, because if your type is unsigned, I don't have anything to do for computing the absolute value. And so most of our functions are just that, something which are, some elements which are protected by some concept over the property of the types going in and the variant of SIMD we want to take care of. And inside, we use this categorization to use if-const expert to dispatch to the proper version. And most of the functions just look like that. Okay, but I lured you in with algorithm. So what kind of algorithm do we do? SIMD algorithm in Eve is one of the stuff that set us apart from other such library. We will be discussing that apart, both in terms of support and implementation. In terms of support, we have quite a bunch of algorithms available right now. We have all the basic predicates. We have all the finds, equal mismatch, variation of transform, and we took a slight departure from the standard there by providing transform to and transform in place, because knowing if we are transforming in place or not leads to some optimization opportunities in SIMD. We have reduce, inclusive scan, again in place or not in place, and remove if, with the caveat that for some architectures currently, like SSE2 and some variant of ARM, it's not 100% optimized. But it is there. Next to that, how does it work? Well, quite surprisingly, a lot like a regular algorithm function call. So we call find if on some vector of int. Okay, so the cool thing is that we are range based, so you can just feed us vectors or range, and we have a helper function to build range from whatever you want us to use, and we pass something that looks like a lambda. Okay, that will be the predicate for the find if, and we got something there. We are looking for negative value inside V, so we got some pre-treatment, and then we got to this point where basically we are loading 4 values at a time, doing some ORs, and trying to find the correct mask. Okay, fine. But that's a bit too much of auto for my liking. So let's see what's actually going on. What's the return type? What are we doing inside? The cool thing is that you pass us a vector, and we will return you an iterator from the vector. We will take care of getting the data properly for the SIMD computation by actually using pointers, but we are kind enough to return you back a vector iterator, right? And then what is going on? Actually, this auto is not required per se. We don't require, like other libraries, that you give us an auto-based lambda that will be called part in SIMD and part in a scalar way. We just require something that consumes whites. And we will take care of the remaining parts in a slightly different way. So there we are waiting for wide of int, because we have a vector of int. And we return this thing, which is logical of wide. And logical is one of our base types that wraps a value. It can be a scalar or it can be wide, to turn it into a Boolean mask. When you are doing comparison in SIMD, when you do a vector equal another one, you get a vector full of false or true, not a single value. Okay, so we have this type to do this, and then we do the operation. Same code than just before. So you can see that basically we take care, all the load up there is to take care of the potentially unaligned beginning of the data, and whenever we are into the tight loop, we are actually unrolling all by ourselves. So this is to get better performances. But sometimes you can actually have something which is a bit more complicated. So there we are calling find if again on a vector of floats. And what we want to do is we call the rat function, which is taking a float and give you an approximation of the best approximation of this float as a fraction. Okay, and so we do this computation, which is a bit complicated, And we say if the denominator of this value is greater than 7, for whatever reason, just an example, we say, yeah, we validate the predicate. Rat is a very complex function. I don't go into the details, but as you can see, it's a bunch of code. And we have like, what? 700 lines. And in this case, one can actually say, okay, am I actually winning anything by unrolling this complex function? Maybe not. So maybe I can actually ask to not unroll. So algorithms are also function object, and you can pass threads to them. And so you can say, you know what? Let's unroll by nothing, by 1. Just don't unroll, please. Okay. So we were at 700 something. Okay, let's. Oh, I did that yesterday. Okay, it's fine. So now we don't unroll anymore. And we are around 200 something lines, 250. But there is another thing I probably don't care. Maybe aligning at the beginning is not useful. Maybe I can just load everything as an inline operation directly. So I can also ask for not having any alignment taken into account. Okay, what about typing the correct words? So I can also ask for no alignment. And then we get a bit more, a bit less code. So and this we got this tight loop there with everything going on with the rats and so on. So we can also control the behavior of the algorithm using threads. So we can actually know if I need to unroll less or unroll more, if I should care about alignment or not, and so on and so forth. Okay, fine. You can tune algorithms. And you can find the, no pun intended, quite strange we put so much effort into getting a vector. It's fine. Find is a very cool algorithm. It's so cool that one thing you want to do is use it more than we are using it right now. If you look at mismatch, the algorithms is basically trying to find the place where two arrays starts not being the same. But if you look at the standard algorithm, it's not written in terms of find. It's its own loop altogether. But what we can say is that mismatch is indeed fine because you have the first two array. You can load a bunch of data from them into a while, and if I put them in a single box using a zip operation that you may be familiar from range V3, by zipping those things, I can actually load those data in a single block where the two whites are next to each other. And the question is, what is the type of this box of two sub-wide? Well, looks like a tuple. So maybe it's just a wide of tuple. Also, QB tuple is our own implementation of tuples that compiles faster than the standard one and got better tooling for our usage. So it's a wide of a tuple of 2 int. And it's a wide because whenever you will do an operation on that, it will just operate on both int at the same time. So I can actually zip those pointers, load them as a wide of tuple of int, and then do my mismatch. And once we have these zip abstractions, you could also change the way you are looking at the implementation of mismatch in terms of interface. So the standard iterator-based mismatch looks like this. You take your both first iterators, the iterators to the beginning of the second range, and your predicate, and you return you a pair. What we do is we await for 2 ranges, any kind, okay, and a predicate, and what we return is a zip iterator. It's an iterator that when you read it, you get the zip of whatever, a tuple of whatever value was inside. And it requires that R1 and R2 are zippable to a single range, so they have the correct properties to be zipped. And as we have zip itself, you could also directly pass the result of a zip to mismatch, and it will take care of it properly and still returning a zip iterator. Okay, fine. But let's see what's going on. Let's implement an MCMP, a vectorized version. Let's have a look at that. It's probably over there. So we take the same interface as the C version, right? So we have 2 pointers to whatever. We have a byte count. So what we start doing is turning both pointers into an actual typed data. So we can actually iterate over char, we compute the end of the range by computing this plus whatever this size is. We construct a as range object that we turn a pair of iterator into a if SIMD compatible range, and we zip it using our zip views with the other range. So zip is able to take two range, a range and an iterator, and so on and so forth. And we just call mismatch over the zip range R1, R2, and it will give us the zip iterator where the mismatch occurred. And now what I do is that if I didn't find anything, that means that the found iterator is basically at the end of the zip range, so I return 0, that I didn't find any mismatch. And if not, I will read the value of the zip iterator to get two values into a tuple, and I will compute the difference, which is the way you are getting the MCMP returns. And one thing we can ask is, why are we using read instead of just the reference operator? The reference operator on zip iterator means that we should have some kind of proxy types, and we don't like proxy types, and you should not like proxy type either. So as it's something very specific, we wanted to have something that is not going to cause issues. So we are going to use read, and we are also write on those iterators. Obviously, it works for all the other iterators because we just call the reference operator, but it's a better way for us to manage that. And so we have the two pieces of our tuple and just do the subtraction. And if we look at the resulting code, well, it's basically what you would get into libc. Where is the loop? The loop is over there. Yeah, we are basically, it's a bit unrolled, and then this is the main thing. So we load a bunch of stuff, compare, and this is all unrolled, and we have a chain of XOR until you find the rest of the computation. So it's basically what libc is doing. Except, well, we write it not in assembly by n. Okay, fine, but what happens with zip if I have different types? I mean, I have a pointer to double, a pointer to int, I zip them, what's going on? Well, exactly what we think is going on. You will end up with a wide of a tuple of int double, and what we do is that to ensure performances, we can compute the proper size for each of those sub-wide, depending on the size of each of the types. On my machine, for example, I can have 8 integers in my wide of int, and I have only 4 double. So what we do is that we will just load in 4 double, which is the smallest natural way of loading those, and we will load 4 int at a time using another type of wide registers. And we do so we can actually take advantage of all the inlining we are doing. And so the cardinal, the number of lanes of a wide of tuple is dependent on the cardinal of the smallest, of the biggest types with the smallest number of lanes. So this is all taken into account, and all operations know how to handle that. The other thing which is cool with zip is that you can fake, let's say, working with more complex types, like, for example, complex. So you have a vector of real parts, a vector of imaginary parts, and you want to do some inclusive scan on complex. Well, you can take both your array of floating points. We have this small tuple of floats that represent a complex that we pass an initializing value there. We zip both real and imaginary parts. We write our operation over wide of complex. So wide is able to handle those kind of tuple naturally. And we do those get to get the parts, and we do the computation. Fine. And then we call inclusive scan in place over the zipped range, using the initial values there, and with this construction, which is a bundle containing the operation and the neutral operation for this, the neutral element for this operation. It's different from the initializing value, and it's quite now required if you want to get your SIMD operation algorithm there to be efficient. And that's the best way we find out to pass this. And if we look at the code, well, stuff are going on at some point. Let's see that. And basically we are where is it? Oh yeah, we are loading the things, we are doing some shuffles. Probably too low, sorry for that. Okay, we are loading things, we are shuffling the values, we are doing the additions, and we shuffle back into the shape and store into the thing. Okay, so it's exactly what we want to do. And as we see, we need 0 there, because that's a neutral element for plus. But 0 is a very special value. So special that Eve provide a function object to generate common constant, and 0 is among them. So you can actually pass 0 this way. And the cool thing is that we know that is a 0 constant. So we can optimize a bit what's going on. And the code is slightly slower, because now that we know that we have a 0 somewhere, we have a bunch of operations we can do differently. So you can use those high-level, here it is, okay, it's like 70, 80 instruction less. You can use those high-level objects to pass more information to algorithms and to function and so on. So fine, we can inclusive scan complex numbers thanks to zip. But well, what about an actual real-life example? Because, zipping complex is fun, but doesn't pay the bill. So this is actually an example that someone contacted us for. So Max Zamarzi is working at Amazon on something which is called OHDB. It's a database system. And what he wanted to do at some point was to be able to walk down a bunch of data in an array and collect the index, okay, of the values that match the predicate. Not the values themselves, the index of the value. And that's something you don't really want to do in SIMD, because index, it's not necessarily the correct type with respect to the type of the data. It's complicated, and you are going to jump all over the place because you are not taking the index of the value that you don't care about. So you need to do some complex operation on that. So contacted us. Dennis worked with him to work on a proof of concept that get implemented into the actual code, and on 64 bits elements, we get a speed up of almost 65.75. You can actually read everything about this experiment on Mark's blog. How does it work? Well, it works using one of our SIMD tricks. So we have a function called compress store. Compress store, take a value in a wide, take a logical, which is a mask of true and false, and a pointers. What's going on is that it will take the value of the wide, take the place where the mask is true, this is in blue there, and it will write the correct value one after the other, without the holes there or the holes there. And it will return you the place where the last value has been written. So that's the meaning of compressed store. You store a wide, but probably with a logical mask, and it gets compressed into the memory. So one can see that you can actually compute the predicate, we get the mask, and then you can work on an index, and then we get the results. Well, exactly what we need. And there is a small optimization that in some case, when you know that you can do it, because you know the memory exists, we call the unsafe version of compressed stores, and just say, you know what, I know that I can actually just write a bit more. So instead of being picky, I can actually write directly the resulting wide, the compressed wide, directly in memory, because I know that I have this small space. And so it got a bit faster. And the code is actually not that terrible. There's a bunch of stuff going on, but okay. So you take the range you want to look at, R, the predicate, a result vector that has some index type, which is an integral type. We check that we have enough data to fit the results. We empty the results. We check that we have something to compute. If not, we return. Usually it's a style things, but for SIMD computation, it's actually interesting because some place, somewhere, we may or may not call memcopy or stuff like that, and memcopy doesn't like to be called on empty range or new pointers. We call Preprocess Range, which is one of our building blocks for algorithms that will prepare your range and turn it into a SIMD usable range. And you can pass different threads. And for example, in this case, I want the range to be prepared so that it takes into account that it will be used with other types, which is IDX type. So please, when you compute the size of the register you use for this range, take into account that I also need to be compatible with those over there. I'm taking the beginning and the end of this range. And if you are doing this, manually in a sequential way, what's going on, you will probably be writing something like I have an index I, which goes 0, 1, 2, 3, and whenever the predicate is true, I store it in the register, in the vector output. But there we are working with multiple values at once. So instead of having I, which is 0, 1, 2, 3, we have a wide I that goes 0, 1, 2, 3, 4, 5, n every time. And you go using this bunch of index at one time. We compute where the actual element stops. We resize the results. And we do a while that say, okay, load the pointers f, pass it to the predicate that gives us my logical mask, use compressor to write it into the output. I advance the pointer by the size of the registers, and I also increment all the index by the size of the register. So 0, 1, 2, 3 becomes 4, 5, 6, 7. And at the end of this loop, if we are not at the end, we will do one pass to clean up the remaining things. But I know that there is a bunch of data I don't care about because let's say I have a vector of 4 elements and I have like 19 elements to process. I have like 3 of them remaining. So we call this keep first mask, that we just keep the first n parts of the white and ignore everything else. And then I do the test and save and compress. Then we resize to the actual number of data and we shrink to fit to return the proper vectors. And everything works directly. And as I say, we got this nice bit up of 5 something. So that's actually interesting because it's a non-trivial algorithm. It does not exist as if in the standard library, and yet we are able to rebuild it. This version is very, I would say that, very fine-grained, because this Y is actually a if algo for each. Okay, we will just run it this way so we can actually look at everything. Okay, fine. Okay, so we have algorithms. We have a way to tune them. We have a way to manipulate range in an interesting way with respect to SIMD computation, and we can write quite easily custom algorithms. Let's go back to this inclusive scan of complex number example. One thing that I don't really like there is that I, as a user, need to know that this is somehow a pseudo-tuple things, and I need to do some get to get my elements, and I need to write my plus instead of just using a plus that was laying around. That's a bit cumbersome. What I really want to be able to do is to write my own complex structures and use it in a SIMD way. Well, let's just do that. So, well, it happens that we can actually deal with structures directly. So we have different ways to do this. We have one which is very external, so you can actually adapt pre-existing types. But this is the intrusive version when you are actually writing your own complex, your own structures for vectorization. So you do your structure, it's called CMPLX, and you use this struct support base class, that is basically some kind of CRTP things, that says that basically CMPLX is a float and a float. So it's 2 float. Then you can write helper functions like re and im to access to the sub-element to get the real or the imaginary value. And we use this like concept that says that this function takes anything that basically looks like a complex. It can be a one scalar CMPLX, or it can be a wide of CMPLX. It takes both. We take the value, we extract whatever we need to extract, and we get the proper element. Same for the imaginary part. Struct support gives you access to a lot of pre-made operators, including comparison and ordering, but we know that ordering makes no sense on complex, so let's remove ordering by using this opt-out system. Then I can write a compound operator like plus equal, and as soon as I have a plus equal, I will have all the variant of plus directly. So this gives me a way to get plus equal and plus between complex. Okay. So what is plus between complex? We extract both parts, we do the computation, and return the computed value. We can also provide unary operator like operator minus, but we don't build minus equal from those two. You need to provide it directly because we need to be able to optimize every pieces. You can also give us a stream operator, and you just have to write it for the scalar version, and we will turn it into a vectorized display later on. And if you need to overload a function, like let's say you want to compute the absolute value of a complex, well, you have this tag dispatch system that let's say, okay, for these types, for this function, this is what I want to do. And now when you will be calling if apps on the complex, it will go into this. Okay, how does it help us? Well, turns out that as soon as I have these things, I can also store the complex pseudo-structure in a SIMD compliant container, which is called SOA vector, that will take care of storing everything properly for vectorization for these tuple-like objects. So now actually my inclusive scan complex just become normal. I having a SOA vector of complex, I have some init value, and I just call inclusive scan in place. Because by default, inclusive scan use plus, which I have, with 0, which I know how to produce from the rest of the data. And the cool thing is that the code is actually slightly better because it knows more about what's going on. You see, it's less overread before, because SOA vector provide a properly optimized iterators and range supports. So we can actually do pseudo-structure object computation like that. And we can do this with whatever we want. So this is a small physics simulation. We have bouncing balls in 2D. Okay, a ball has a mass, it has a position, and it has a speed. And I also have a count of how many times I bounce it back. So I just make a ball, do my access to my elements. I don't need anything else. I will write a small function operator that say, okay, give me a ball or something that looks like a ball. I will update its position, I will update the speed, I will check if it bounced. And if it bounced, I will update the speed again in a different way. I will just flip it with an elasticity coefficient. I will count the fact that I bounce. And then I will select which part of the balls are actually bouncing back. So if my position is lower than some arbitrary value, then I guess I bounce and I return the bounce state. And if not, I'm returning the falling state. But the thing there is that everything there, B and scope P and its operations there, are done on a light ball. And light ball can be just a ball or a vector, a SIMD vector of balls. So that means that all this physics is getting vectorized automatically. And what you do, well, you just take transform in place and you call behavior on the balls that you take as a parameter there. And then what you can do is that you can actually use remove if to remove all the balls that bounced too much and then remove them from the actual SOA vector, like you will be doing with a vector. So I can actually write high-level structure-based and algorithm-based code using if directly. I can adapt an arbitrary structure, I can build a structure that can be vectorized, and everything gives us the proper level of code generation. So let's have a look at the deep loop. We are loading values, we are doing all our physics, we have the blend, which is the if-else, and we store the results, and we do that a couple of times because we unroll by 2. What I wrote is, I do something with my physics object, nothing else. So that's also something that we are quite happy with, so we can actually vectorize more than just a bunch of array of floating points. Okay, let's say now you actually want to use this. We hope. Some practicalities. What about bugs? Yeah, maybe. As Dennis likes to say, the API surface of Eve is basically the size of Mars. So maybe we forgot an interaction with different threads or different things. We have an extensive set of tests for precision and numerical correctness. So this part is usually well-rounded. But we are not, we are not perfect, so maybe we forget something. What about API stability? Not yet. We are still breaking things to find the proper way to express some stuff. We won't be changing radically everything, but there is small adjustment to be made there and there. So, well, we usually try to make them evident in the release notes. So normally it should be okay. What you should be doing? Well, focus on the critical performance component of your application or library and just try to work on that. You can try to build a standalone library that will provide you the vectorized version of your computation kernel. As I say, the variant of the the operation are selected at compile time, but we have a support for finding them at runtime. And so you can actually use dynamic linking library if you want to pick at runtime the best architected version of your algorithms. And of course, you can contact us if you are stuck somewhere. There is similar libraries, of course. We are not the first to do that. Well, the most well-known is probably VC, which is stated to be standardized at some point. And there is stuff like XSIMD, TSIMD, insert a random constant SIMD. There's a lot of them like this. We consider that the basic things those libraries do, we do roughly the same. There is no surprise there. I mean, there is only so much way to do A plus B using SIMD, if you see what I mean. We are different in the way that we are this no old bound C++ 20 API mindset that we want to get something that is the most easy to use and the most efficient. So we are not looking too much at how it is done usually. So we try to a bit innovate. And that's what we can see in the algorithm part or in the support for structures. You also have stuff like SIMD everywhere, which is a different kind of beast in the sense that it's just a library that tries to homogenize intrinsic. So whenever you have an ARM code, you can just compile it with SIMD everywhere, and it works on SSE2 because it does the instruction wrapping and so on. But it doesn't have any high-level systems. So some shout-outs. First to Jean-Thierry Lapreste, which is our math guy. He do maths I don't even understand. He's a guy that worked on a lot of our numerical algorithm and numerical correctness. So a big thanks to him because it's a thankless job. A bunch of people over Stack Overflow in random order, Acquit, Peter Cordes, Z Boson, and Stephen Cannon that help us a lot or inspired us a lot in some cases. Thanks to them for their help. We ripped the SOA vector idea from Unity, which is a great model to do that. Thanks for them to have the idea before us. And if you want to dig into the details, you can have a look at the first talk about Eve by Dennis at Meeting C++ 2020. And of course, well, you can, as I say, find the slide over there. This is a link to the GitHub if you want to have a look or just fulfill an issue because something doesn't work. We are present on the hashtag include Discord. We also have our own Discord if you want to discuss some things. We are also on the Slack, either me or Dennis. You can find us at our email or on Twitter. So don't hesitate to contact us. So thanks for your attention. I think there is a bunch of questions. I think we still have time. Well, not much, but let's do that. So one question in Zoom. So is there a fallback to a non-SIMD version in case certain intrinsics do not exist on a given architecture? Yes, that's done automatically. Either by combining other existing intrinsic, because sometimes that's only what we need to do. And if something does not exist at all, we have an internal way to just map the equivalent scalar version of the code over all the elements of the vector. So whenever you run a function on a wide, it's basically working correctly. And sometimes you may get some kind of emulation if needed. That's something we are also trying to find a way to automatically document so people knows when and how some function can be in, let's say, a degenerate states. So, do you have any plan of collaborating, trying to include Eve within performance portability library for HPC, just as cost, for instance? Well, why not? We've been contacted by people from HPX to do exactly that, so we'll probably start doing this soon. I think it can be done. I don't see any issue with doing this. Now we have quite a stringent a set of constraints, especially within the compiler version and so on. So that's maybe for them to see if they want to do that. But yeah, that's something we hope to do. Another question about, do we have a class similar to interleaved memory wrapper for unpacking pixel to vector of components and backwards? I think that's exactly what our wide of tuple does, actually. Because when you have a wide of tuple, you fill it with values that are actually the tuple scalar instance, but we store them as desinterleaved data. So when you have a wide of tuple of int float, it's actually a wide of int and a wide of float, and everything is done so the conversion is transparent. We also have specific interleaving, desinterleaving functions. So if you really want to do that, and usually what we do is we advise people to use the higher level system, which is the SOA vector things. We have a bunch of shuffling functions that actually help you to do that if something is not exactly as you want, because usually the issue is that your data are interleaved and you want to desinterleave them to put into a wide and back and forth. Okay. So the other question is dynamic dispatch. Yes, but not at the, we don't support dynamic dispatch at the function level. What we support is that you can actually compile your if-based kernel multiple times with different options, either in a single binary by using some function overload systems that we support, okay? And then you can actually have a bunch of if-else depending on what you find out at runtime and call the proper one. We have an example for that we made for someone, and I should clean it up and put it on the GitHub so people can have an actual complete buildable example of dynamic dispatch. But we do have a support for that. It's not automatic. It needs a bit of work, but not much, considering that the most complex part is basically finding out which version of the instruction set you have, and we have a wrapper for that. So I should work a bit more and get that running, but we have something like that working and working properly. So I will probably add that in the example folder of the GitHub soon. An OpenCL backend. Well, I wish we have an OpenCL backend, but OpenCL is, or how to say that, because this is on tape. I mean, it's the same question as if you ask me, do we have a CUDA backend? Sort of. It's not the proper programming model we aim to wrap. The other issue with OpenCL is that means that we will probably need to have some kind of expression template supports to build up large expression and then turn them into an OpenCL kernel that we then compile. For me, it's not the correct. I mean, if you want an OpenCL backend, you should have an OpenCL backend upward at the array level. That's not what we are trying to provide there. I mean, it's like CUDA. You could actually look at the GPU as some kind of SIMD system, and why not adding Eve over, for example, CUDA warp? But then you eat up the problem of compiling code properly for this kind of architectures. So that's something we thought about it. We put them somewhere for like maybe far later, because currently it doesn't quite fit the look and feel of what we want to do.